Okay, got it. Okay, so we've been talking about expectation and variance. We define, given a random variable x, we define the expectation to be the summation of x of I times p of x of I, or all possible I values. And then we define the variance, which is always positive or zero, to be a special kind of expectation. It looks at the differences between the squares of the actual observations and the mean. And this is also called mu, or mu sub x. And we showed that this is equal to, it's often easier to compute it the following way: e of x squared minus e of x quantity squared. And then we developed the various properties, for example, expectation, the expectation of the sum, the expectation of a sum is equal to the sum of the expectations. And properties like E of AX plus B in general is just AE of X plus B, the linearity property. And we also looked for variance. We know that for the variance, translation has no effect on it. That was an important property, variance. And more generally, V of AX plus BY, where A and B are constants, turned out to be A squared V of X plus B squared V of Y plus 2AB E of XY minus E of X E of Y. Okay. And in the special case, when X and Y are independent random variables, then this term right here would be zero when independent. Variance is always a positive number. Variance is always measured in units squared, whereas the standard deviation is a square root of the variance. And then the last thing I did the other day was I talked about Markovs theorem, which was a very rough approximation. And I proved the following theorem. I want to use the same notation I used then. I think I said it in one of suppose X is a non-negative random variable. So X is either zero or positive. And suppose, did I use the letter A? Or I want to stick to my notation here. That's important. Okay. And let C be any real number of any positive number. Then Markovs theorem says the following. It says the probability that the random variable X takes on a value greater than or equal to C, or takes greater than or equal to C, will always be at least the expected value divided by C. This was Markovs theorem. And it doesn't say very much. You don't know what the distribution is. You don't know what X is. All you know about x is it's non-negative, and you know c is a positive number. Then if you want to estimate the probability that x is greater than c, it turns out to be less than or equal to e of x over c. I'll compare that in a minute with an example I did the last time. I'll repeat it. And it turns out that this isn't really the important theorem. It's useful, but it's not as important as say, Chebshev's theorem, which we're going to state in a minute. And then we'll look at these. And these two theorems are really just important to prove other theorems. They're not very powerful results, but they give us a little bit. And I think I like to use the expression, the less you know about a distribution, the less accurate your approximations are going to be. So here you don't know very much about the distribution. All you know is that it's you know the mean, and you chose some number c. So for example, a trivial example, I think I have one here that I'm going to do. Suppose I have the following. Okay, suppose x is the random variable which measures the life of a light bulb. So by that I mean how long it lasts before the light bulb goes out. Okay, and suppose we know the average lifetime of the light bulb. That's what E of x would be is 1,100 hours. What's the probability that the light bulb would last at least, say, 1,000 hours? So you don't know much about this light bulb. All you know is its average lifetime is 1,100 hours. Well, so we're given, what did I say here? Okay, so I'm telling you the average. So what's the probability that this light bulb will last more than 1,000 hours? It'll be less than or equal to the expected lifetime of the light bulb. Oops, this shouldn't be here. Divided by C, which is 1,000. This is a stupid result because of the numbers. This would turn out to be 1.1, which is trivial. All probabilities are less than 1. So I made up a lousy problem. I'll refine the problem in a minute. It's pretty certain that it's going to do that. So maybe what I should have done is, let's, instead of 1,000 hours, let's say 1,200 hours. Okay. If I made this 1,200, then this would be it would be less than E of x, which is 1,100, divided by C, which in this case is 1,200, which is 11 over 12. It's not the greatest problem, but it illustrates the idea. But I'll do better for you in a couple of minutes by looking at another example. Okay, so we have Markov's theorem. So again, so Markov theorem says the probability that x is greater than or equal to c is less than or equal to E of x over c. So that's Markov. Now I'm going to write it a little differently in a minute. When I prove Chebshev's theorem, I'm going to take the same result, and instead of c, I'm going to replace c by the number a squared. Okay. So if I do that, then Markov's theorem would be probability x is greater or equal to a squared is less than or equal to, say, E of x over a squared. Or if I had another variable instead of x, if I called it y, I could replace x by y. So with that in mind, I'm going to use this form in a minute. I want to prove Chebshev's theorem. So Chebshev says the following. So we're given the random variable x, and we're told two things here. We're told its mean is given, and its variance is given. Okay? Then, for any number a greater than 0, we have the following result. The probability that x differs from its mean by at least 8 units is less than or equal to sigma squared over a squared. I'll interpret this in a second. So here's one formulation. So for any number, this is going to be true. Now we'll interpret what this means in a moment. But I want to remark that there are 3 different ways of writing this theorem. So I'm going to prove number 1. Notice number 2 is just a complement. If I take the complement of this, it would be the probability that x minus mu is less than a. That'll be greater than or equal to 1 minus sigma squared over a squared. That's another formulation of the theorem. All I did is replace it by its complement. There are 2 other ones that you'll often see. That is, suppose I let a be k times sigma, where k is positive. Okay, sigma is always positive. Then we get the probability that x minus mu is greater than or equal to k sigma is less than or equal to 1 over k squared. How did all I did in this problem up here is I replaced a by k sigma, which is still a positive number, and the complement of this result is just p of x minus mu less than k sigma will be greater or equal to 1 minus 1 over k squared. And I'll look at this in a minute, different interpretations, but they're all the same thing. If you know one of them, you know them all. So I'm going to prove the first one. Okay. So let's rewrite Markov's inequality as follows. Firstly, observe, where am I? I lost my place. I'm going to write p of y greater or equal to a squared is less than or equal to e of y over a squared. This is Markov's inequality with x replacing y and c is being replaced by a squared. Now, let's let y equal x minus mu squared. That means y is a non-negative random variable. So I can apply Markov's theorem. And by Markov's theorem, okay, right here, I get p of x minus mu quantity squared greater than or equal to a squared is less than or equal to e of y let me make this a little smaller so you can see. Yeah, hold on. Less than or equal to e of x minus mu squared over a squared. But remember, e of x minus mu squared is sigma squared over a squared. So I've just shown that the probability that x minus mu quantity squared greater than or equal to a squared is less than or equal to sigma squared over a squared. Now, this is equivalent, this event right here is the same thing as saying the probability that the absolute value of x minus a, of x minus mu, I'm sorry, is greater than or equal to a. I just took square roots of both sides, is less than or equal to sigma squared or a squared. Okay, so we've proven, oops, where'd you go? So I've proven that probability of the absolute value of x minus mu less than or equal to a is greater than or equal to a is less than or equal to sigma squared over a squared. And perhaps the other most useful formula for this is if I let a equal to k sigma, then we can write the result as so 1 over k squared. So these are really the two most common formulations. The other two are just the complements of these. So let me see what we can do with this. So we've proven this theorem. This is Chebshev's theorem. It's not going to be that useful, as you'll see. I'll show you why we use it in a little bit, but we need to have the theorem for some purposes. So let me again, let's look at a couple of examples, and then show you that it's not a really very good theorem at all. So here's the example I want to look at, the one I did a minute ago. So let's assume x is a random variable, okay? It measures the lifetime of the light bulb. And moreover, I'm telling you that the lifetime of the light bulb, that's its average lifetime, is 1,100 hours. And its standard deviation is 120 hours. What's the probability that this light bulb will last between 860 and between 860 and 1,340 hours? Now, I want to tell you right before I begin, I rigged this problem to work with Chebshev's theorem. In the next example I'll show you how you can use the Chebshev's theorem when it's not natural. You got to be a little clever. Okay, so notice the first thing is the mean is, what's the mean? 1,100. So let's suppose I subtracted from the inequality. This is equal to oops, come on. Notability. This is the probability that x minus 1,100, that's the difference between the mean, is now between, what's it between? 240 and minus 240. Right, we do the subtraction. Or the probability that the absolute value of x minus 1,100, come on, is less than 240. And notice 240 is 2 times sigma. Right, it's less than or equal to 2 times 120 hours. So now if we look at this, so this is essentially probability that x minus mu is less than 2 times sigma. Remember, sigma in this problem is 120. Well, according to Chebshev's theorem, this will be this probability is here. Let's go to theorem. We're looking at in this form. What do I have? The one I'm looking at is less than. It's the complement of this result, right? Right here. So this would be 1 minus 1 over k squared. And what is k in this problem? K is 2, which gives me 0.75. So the probability that this light bulb will last between 860 and 1340 hours is about 3/4. Now, make a couple observations here. I rigged this problem. This problem was rigged so that we had this symmetry. Notice between minus 240 and 240. So we're able to write it in this format. So we're able to apply Chebshev's theorem. That is, it was symmetrically spaced around the mean. What if the data wasn't given that way? What would you do? Well, you have to be a little bit clever, and I'll show you one way of being clever. And in fact, this says that the probability that this light bulb will last at least 2 standard deviations above the mean. In this case, the standard deviation was 120 hours, right? So 240 was 2 standard deviations, 2 times sigma. So the fact that this would last, the probability that this would last within 2 standard deviations of the mean turned out to be 75%. Now, all we know about this distribution is its mean and its variance. It turns out if X was actually normally distributed, which it isn't here, I didn't tell you it was, then the probability might have been 95%. You don't know too much if you don't have more about the distribution. Let me do another example just to show you again how bad these are as approximations, but they have some use. So the problem I did the other day, which I didn't finish, was the following. I'm going to toss it. X is the number of spots when you toss a pair of dice. And I showed you, in fact, I worked out on page 111 in the text that the sum of the spots on average is 7, and the variance turns out to be 35/6. So let's assume we have this information. And if you want to see it worked out, page 111 in the text. So suppose I ask the following question. Using Markov, estimate the probability that the sum of the spots on the dice, if you toss them, is greater than or equal to 10. That's the first question. Well, according to Markov's theorem, this is equal to at least what did I say, 10? Let's see what I said. Okay. Well, according to Markov, this is going to be at least I'll delete that. Less than or equal to the mean E of X, which is the mean, divided by C, which is 10, which is 7/10. Okay, that's what Markov's result would say. Remember, Mark said the probability that X is greater than or equal to C is at least E of X over C. So that's where we got 7/10. So the probability that it exceeds 10 is less than 7/10. Okay. Now let's do it exactly. Well, the probability that x is greater or equal to 10 is equal to the probability that x is 10 plus 11 plus 12 probability x is greater than x equals 10. In order to get a 10, what are you going to get? A 4, 6, a 5, 5, and a 6, 4, which is 3 out of 36. For an 11, you got a 6, 5, and a 5, 6. And 12 is 1. 1, 6, which is about 0.167. So here's the exact answer. Here's the answer I got using Markov's theorem. It's true that according to Markov's theorem, the probability that x exceeds 10, the sum is greater than 10, is less than 0.7. But in fact, it's much less than 0.7. It's 0.167. So even though it tells you a true inequality, it's not very accurate. Now let's compare that with Chebshev's inequality. And here I'm going to be a little bit clever. Let me see how clever I was. Now let's use Chebshev. So the probability that x is greater or equal to 10. Now here's where I have to be a little bit clever. I have to get it in terms of the mean. The mean is 7. I can rewrite it this way. Again, I'm going to be clever now, okay? So this is certainly true. I just manipulate inequality. And if I want to make this symmetric, I know this will be smaller than the following. Or x minus 7 less than minus 3. Why is that true? Well, what I've done is I enlarged my space here. I've added more possibilities. So what I want is going to be smaller than this enlargement over here. But this enlargement I very cleverly can rewrite as x minus 7 in absolute value is greater than or equal to 3. That's another way of saying that. Now, we know from Markov the probability x minus mu is greater than or equal to k is less than or equal to sigma squared over k squared. And in this case, sigma was 35 over 6, and k was 3. So what does this give me? This gives me 0.648. Now notice 0.648 is more accurate than 0.7, but it's still nowhere as accurate as the exact answer of 0.167. So the point being, you don't really get very accurate results from Chebshev's inequality. But it will give us some theoretical results, and that's where I'm going to use it. I know students don't always appreciate the theory that we do in these courses, but one should see this because we want to make another observation that we made earlier this semester. So let me build on Chebshev's inequality a little bit. So I wanted to find a new random variable. Let's suppose I have the following random variables: x1, x2. I have n random variables. And let these random variables be n independent, identically distributed random variables. By that I mean, say I perform the same experiment n times. That's one way of doing it. So we have a new random variable which we're going to call x bar. It has a name. It's called the sample mean. And I define x bar to be the sum of all of these x's divided by n. Take their average. Again, it's called the sample mean. The first thing to observe, by the way, we're going to need this a lot later on in the semester, is E of x bar would be E of the sum by the way, I should remark up here, this means E of each of these x's is the same. I'll just call the common value mu. And the variance of each of these x's is sigma squared.
Professor, sorry to bother you. Under the x1, x2, what is it?
I'm sorry?
Under x1 and x2, and then it goes to x to the n, what is
Divided by n.
divided by n?
X1 plus x2 plus x3 plus xn, everything divided by n. I'm taking the average of these.
And then under that, I couldn't read your handwriting. I'm so sorry. Is that supposed to be n is an independent?
These are, we have n independent, identically distributed random variables. So every one of these random variables is exactly the same. For example, maybe I'm doing the same experiment n times. Okay?
Okay.
And each of these x of i's has the same mean and the same variance. So here's what I want you to do. I'm going to give you 1 minute or 2 minutes. I want you to use the properties of variance and the properties of expectation to simplify this expression. Okay, I'll give you a minute. See if you can simplify these two expressions, and then I'll pick it up from there. Okay. Let's work this out now. I'm going to use the linearity property of expectation and variance. So E of x bar is equal to, I can take out the constant first, the 1 over n, and then what's left is E of x1 plus all of these. But the expectation of the sum is the sum of the expectations. And that gives me mu n times, right? There are n of these are identical. So E of x bar turns out to just be the common value for all of them. So the average expectation just turns out to be the average of the sample mean, I should say, E of X bar is just mu. On the other hand, when we take the variance of a sum, since they're all independent, it's the sum of the variance. So this is going to become V of X1 over N and so on. And when we do that for the variance, when we take out a constant, we get a square. But each of these is sigma squared, I should say. So the variance is of X bar is 1 over N squared times N times sigma squared. So the variance is just sigma squared over N. So let me just summarize these two results. He's going to come back to haunt you later on this semester. Let's make sure we remember them. So we've just shown that if we define X bar to be the average of these identically distributed independent random variables, E of X bar is just their common value mu, and V of X bar, also called sigma sub X bar squared, is equal to sigma squared over N. Okay, now why do I want to do this? Now, suppose I apply, so this is an important result, and we're going to need this later on, especially when we get down to the central limit theorem towards the end of the course. Now, let's suppose I apply Chebshev to X bar, okay? Well, according to it said P of X bar minus mu, this is mu sub X bar, let's stress that, is less than or equal to A is less than or equal to sigma squared over, well, let me just, here, let me say it this way first. The formulation I used. This is sigma squared over A squared. Now, in this case, let's just rewrite this a little bit. All the mu's are the same. Now, I just showed you that sigma is going to equal to sigma squared over N. So this turns out to be less than or equal to sigma squared over N divided by A squared. Or for this mean, the probability of the absolute value of the sample mean minus mu is greater than or equal to A is less than or equal to sigma squared over A squared N, where A is any positive number. Okay, now suppose we let N get very large. So this inequality, look what this says. This says a difference between the sample mean and the actual mean. The probability that this exceeds any number A, this will approach, as n goes to infinity, the right-hand side will approach 0. So this says if you repeat an experiment many times, the difference between the actual mean and the sample mean will approach 0. So that says in the limit, the average value of the sample mean, it will actually be close to the theoretical mean of the distribution. Now that's a pretty interesting result in this sum, by the way. The fact that the sample mean approaches the actual mean. So again, let me reiterate what we've just proven with a very weak inequality, with Chebshev's inequality. Using Chebshev's inequality, we're able to show that if we repeat an experiment essentially in identical conditions n times, and we take the sample average will as n gets large, will approach the actual mean of the distribution. That's an important result to know. Let's take that a little bit further. Let's suppose in the same example, each of these x sub i's take on 2 values, okay? X sub I is equal to 1 if some event A happens, and 0 if the event doesn't happen. First, let me make some observations about a random variable of this type, okay? So I'm defining x sub I as follows. We have these we've done this problem n times. We've n identically distributed random variables. Whenever A occurs, xi is 1. Whenever A doesn't occur, x sub I is 0. First thing to observe is, and by the way, if this happens, of course, with probability, we'll just with probability P. Okay. So the expected value of x sub I will just be 1 times P plus 0 times 1 minus P. That's the complement, which is P. And E of x sub I squared would be 1 squared times P plus 0 squared times 1 minus P, which is also P. So notice we have E of x sub I is P, and V of x sub I is E of x sub I squared minus E of x sub I quantity squared. This is equal to P minus P squared, P times 1 minus P, or if you like, I'm going to call Q 1 minus P, PQ. So I have for this kind of random variable, E of x sub I is P, and V of x sub I is P times Q. Let's try to remember this. Okay, so now if we go back to what I did a minute ago, I want to use the same notation in text. Notice V of x sub R, it will then be, remember what x sub R is now. V of x sub I was PQ, or P times 1 minus P, doesn't make a difference which one you do it, okay? Something's bothering me. And E of x bar. Remember, V of x bar was equal to sigma squared divided by n, and E of x bar was equal to just mu. In this case now, where that I've just considered, where the random variable x sub I is either 1 or 0, what does this mean? This will just mean that this is equal to PQ divided by n. So we have the mean and the variance here, and mu, by the way, was equal to just p. So again, let me backtrack before I state the result. I just looked at a special case of the sample mean where I found above, I could write the probability up here. See it? And now I'm going to look at the case when each of the x sub i's are if the event happens is 1, if it doesn't happen, it's 0. So if I substitute that in then, firstly observe the expression I had before was P of x bar minus mu greater or equal to A. Is that what I had before? Was less than or equal to sigma squared. What was my result? Sigma squared over NA squared. Okay, now, oops, where's this going? So let's look at this expression a little bit more closely. X is really nothing more than the relative frequency of the number of times this event A happens. Remember, x sub I is 1 if A happens. So the total number of x's, the total number of ones, is the frequency that this event A happens. Mu was its mean, is its probability. So I'm just rewriting this expression we had a moment ago. And this was less than or equal to P times Q. Sigma was P times Q over N A squared. So look what this says. Again, I'm using Chebshev's inequality to write this. If I take this experiment, if x sub I now measures is 1 if whenever the event A happens and 0 when A doesn't happen, then the difference between the relative frequency and the actual probability of an event happening, the probability that exceeds some number A, will always be less than or equal to PQ over NA squared. This means as n gets large, again, the number of times the relative the closeness of the relative frequency to the actual probability of an event becomes very, very close. And that's exactly what this inequality says. So this says when we talked earlier in the semester about the idealized relative frequency, what we mean by probability, essentially it's what happens when you repeat an experiment very often. This gives you what's called the weak law of large numbers, meaning as n gets large, the actual probability of the event gets very, very close to the actual probability. And you can do even more by this. So you can estimate how good the relative frequency is by means of this result. Now you can do even more. Suppose you don't know the probabilities. You don't know little p. Well, remember, the less you know, the worse your result's going to be. But notice if you look at p times 1 minus p, or p times q, if you plotted this, that's a parabola that looks like this. This is p, and this is p times 1 minus p. And notice this parabola has a relative maximum when p is equal to a half. And at this value, this is a quarter. That's called calculus. Remember that? Or the vertex of parabola. So we know that this number here is always going to be less than 1/4 n a squared. So even if you don't know p, you can still estimate the difference between the actual probability and the relative frequency. It's not going to be a great estimate, but n would have to be much larger. And I actually work out an example for you later on in the text. But I don't want to talk about that. How am I doing time-wise? There's another idea I want to finish here. Yeah, okay. I want to talk some more about these random variables. Now, again, Chebshev's inequality isn't so useful. I want to emphasize that. But it helps in proving theoretical things. We've just proven, for example, that if n gets very large, the difference between the relative frequency and the actual probability is small. And that's important to know in probability theory and statistics. Notice before I defined a random variable, I'll just call it x for now. It's defined to be 1 whenever the event A occurs. Maybe with probability, it's a little too smudgy. And maybe this will be probability P, and it'll be 0 when A does not occur. Such a random variable has a name. It's called an indicator random variable. It's called an indicator because it tells you when something happens. It indicates the occurrence of the event A. Now, I just showed you a moment ago that for such a random variable, E of x is equal to P, and V of x is equal to P times Q, where Q, remember, is complement. Okay. I want to talk about this indicator random variable and show you how it's sometimes pretty useful. I guess I'll proceed with an example. So I guess it's important enough for us to say this is a theorem. If x is an indicator random variable, E of x is P, and V of x is P times Q. Now, let me show you why this is an interesting result, why it's sometimes useful. And let me begin with an example. Let's suppose we have 8 different pairs of socks. That's 16 socks in total, right? And they're going out to the laundry, okay? And 10 socks were returned. Determine the number of expected pairs of socks that are returned. Okay, let's make sure you understand the problem. So we have 16 socks, 8, what did I say? I'm sorry, is that right? Yeah, 8 pairs of socks. You send them out to the laundry, and it turns out only 10 socks are returned. How many of these are expected to be pairs? So this is an interesting problem. The first time I saw this problem, I never did it this way. I did it by brute force, but it turns out there's a very clever way of doing it. And we'll do the following. We'll define the random variables as following. Let x of I equal to 1 if the ith pair is returned, otherwise 0 if it's not returned. Okay. So, you know, it amazes me that I get all these phone calls telling me they want me to take out a warranty on my car or something. Okay, so x of I is 1 if the ith pair is returned, it's 0 otherwise. So x then would be x1 up through and including, there are 8 pairs, right? So this would be the number of pairs returned. If x1 is 1, meaning the first pair is returned, you get that pair. If x1 and x2 are each 1, you get 2 pairs and so on. So the maximum number of pairs that would be returned would be 8. The problem is to find e of x, which is equal to e of x1 through x of 8. The expectation of a sum is the sum of the expectation. And each of these stocks are identically distributed. So E for each of these is going to be the same. So this is just equal to 8 times any one of these. Let's say E of x of 1. Now, or this is equal to E of the probability that x sub 1 equals 1. Let's backtrack on this. So again, remember, we showed a moment ago that for an indicator random variable, E of x is always equal to its probability. So the probability that it's returned, the probability that it's 1, is what we want to find, because that's equal to E of x, and then we multiply that by 8. Now, there are a total of 16, so we want to find basically the probability that any one of the pairs is fully returned. Doesn't make a difference which one I do. Well, we know altogether there are, how many were returned? 10, okay. We're getting 10 socks are returned. So from the 16 socks, we have to choose 10. That's the number of ways we can choose 10 from the 16. And the probability that the first pair is returned means from the first pair, I get 2 from the first pair. And then from the remaining 14 other socks, we get 8 more. Which, by the way, I worked out in the text, turns out to be 3/8. So based on these numbers, E of x is 8 times P of any one of these probabilities, which turns out to be 8 times 3/8, or just 3. So on the average, you expect to get 3 pairs returned. Okay. This is the purpose of this problem was to show you that using these indicator random variables, sometimes problems that were difficult can be made very simple. Let me give you how's my time? Another example of this. Yeah. In fact, I'll show you a different way of thinking about it, but one can do this in a similar way. Let's suppose you have a well-mixed deck of cards. Okay. So I have 52 cards. On average, how many cards do I turn over before I get to the first ace? Okay, so I have 52 cards. How many till I get to the first ace? Now I could do it. I'm doing this because it's just an interesting variation to something called the symmetry principle. I can do this problem in very much the same way as I do it, as I did this last problem. In fact, I think this is a problem right from the text. And I work it out on the answer sheet. If you want to see it, where is that somewhere? It's problem number 15 in the text. But I'll show you an interesting way of doing this problem. Okay. So if you look at the solutions that I work out in the text for you, look at the reference. I think I do it there a couple of ways. But what I want to do is I want to show you a very, very clever way. So we have these 52 cards. Okay. Now, let's suppose the deck is very well mixed. So then you would think that these the aces would be distributed equally throughout the deck. Agreed? I mean, this is an assumption. So oops, I lost my own thing. Let's try it again. So if these aces are equally distributed among the other 48 cards, we have 52 cards. There are 48 regular ones, right? So on the average, there would be, until I get to the first ace, there would be how many cards? Well, if I divide the 48 into, let's see, the first 2, 3, 4, I would have these 48 remaining cards. So the first ace would be roughly 1/5 of the way in, right? The 4 aces would divide the deck into 5 pieces. So the first ace would be roughly, there would be 48 divided by 5 cards before you got to the first ace. Now this, I'm assuming a symmetry here, which by the way is 9.6, right? So on the average, you would turn over 9.6 cards before you get to the first ace. Now that's a very interesting way of doing a problem, and what is it based on? It's based on the notion of symmetry, which one would expect to happen if n were sufficiently large if you did this problem many times. What's interesting to note though, is if you try this by brute force, bingo, it's 9.6. You try using the indicator method, it's going to be a 9.6 as well. It's just an interesting result that everything gives you the right answer, even the notion of symmetry. Okay, so the key thing here, and what I've done so far is, oops, we have 2 results. We have Markov's theorem and we have Chebshev's theorem. These are generally used to prove theoretical ideas. And we've also introduced a notion of an indicator random variable. Occurs. A does not occur. And for an indicator random variable, we're going to see that a special case of an indicator random variable is called a binomial random variable. also called a Bernoulli trial. Bernoulli. It's an important case we're going to look at in some detail. Basically, when something happens, it's a 1. When something doesn't happen, it's a 0. For example, suppose I toss I flip a coin. I flip a coin once. If I get a head or a tail, that would be an example of a binomial or a Bernoulli trial. You will see that these indicator random variables show up a lot. The other net we're going to need is X bar, when all the X's are independent, identically distributed. You need to remember that E of X bar will just turn out to be the common value mu. V of X bar will turn out to be the common value divided by n. These are the results I showed today. This is going to come up again when we do lots of problems involving the so-called central limit theorem. It's a prime example for work that's going to show up there. Okay, anybody have any questions about anything I've done? I understand that the theory part for some people is a bit confusing. You'll work out some problems, you'll get a better feel for them. I could stop the recording now and then I could just take questions and stuff. Let me get back to Zoom. I won't stop the recording.